Okay, so for those of you watching on video, I just started the recording now. Lost about 2 minutes. What we talked about already is really unimportant in terms of the lesson if you're watching this because you're away. We're reviewing some stuff from Math 10C here, and we have to convert all of the following in review number 1 from entire radicals to mixed radicals. It really ought to say to mixed radicals in simplest form, but that's implied. Why are these called entire radicals? They're called entire radicals because everything is entirely underneath the square root sign. A radical is something that contains a radical symbol, which is the square root symbol. So, for example, something like this is considered a mixed radical because part of the numbers are under the radical and part are not. And again, remember everybody, this is review as well, you should know this, 44 is called the radicand. And that language, before I get to the actual question, that language is important. It's important you understand when I say, oh, we need to do something to the radicand, that I'm talking about what's underneath the radical sign. So there are 2 ways in which we can solve this problem. And I'm going to show you a way that maybe your Math 10 teacher showed you, and you maybe shunned that idea and you threw it off to the side because there's a quicker approach. The reason I'm showing you the approach that's not quicker is the quicker approach breaks down in a few minutes. We're going to be looking at things that are more complicated where the quicker approach is not as obvious. What your teacher probably taught you at some point is that you can take the number 44, which is the radicand, and write it as what's called a prime factorization, which means we want to write it as a product of prime numbers. What does that mean? It means we want to break down 44 until we can't break it down anymore. So, for example, and I would almost consider this work to get to what I'm about to write to be scrap work or paperwork or work that's going on in your head. I know that 44 is even, so the first thing I do is I divide 44 by 2 to get 22. And then I say, well, I know that 22 can be divided by 2, so I end up with 2 times 2 times 11. And 2 is a prime number. I cannot factor it in any other way other than to say, would you agree 44 is 2 times 2 times 11? Okay. 2 is a prime number. I cannot factor it any further. I mean, I could write 1 times 2, but then I could write 1 times 1 times 2, and I could keep doing that. It doesn't get me anywhere. 11 is prime as well. So what we have here is 2 times 2 times 11. And this 2 times 2 is 4. One of the things you've been taught in Math 10 is that you're allowed, I've got 3 different ideas going on the side here. You are allowed to take the square root of a number times the square root of a number and write it as the square root of the product of the numbers. I want you to roll that around in your head for a second. What does that mean? It means, and this is from Math 10, that root 2 multiplied by root 3 is root 2 times 3, or root 6. And you can verify that on your calculator. If I take the square root of 2, close the brackets on it, and multiply by the square root of 3, close the brackets, I get this number. If I take the square root, on the other hand, of 6, I get the same number. I'm allowed to multiply radicands if I'm multiplying radicals. And that means the opposite is true. What I can do here is I could write this as the square root of 2 times 2 times the square root of 11. Now, why would I decide to splice it at that location to get 2 radicals? The reason is 2 times 2 is 4. And the square root of 4 is not irrational. It's a rational number. It's 2, so you get 2 root 11. Now, personally, I don't really care about these 2 middle steps. What I care about is this step and this step. And I'm going to give you a rule here that will serve us very well in a few minutes. Since we've got a radical, which is a square root, we don't normally write that little 2 there, but we could write square root. The rule is this. Since this number is 2, we're allowed to take out any factor that appears as a pair and write it as a single factor outside. So I have a 2 and a 2. I have 2 2's under the square root, so I can remove them from under the square root by writing only one outside. And that's how we get to this point down here at the bottom. Did you follow that? Would you agree that's probably more complicated than simply saying, well, let's see, what is a perfect square that divides into 44 without remainder? Oh, that's 4, right? Why am I looking for a perfect square? So that I can do this. I mean, doesn't this seem easier? Okay. The thing I did before, this thing, really seems on the left like overkill. But it's going to be very useful for problems later. Okay? So the answer is 2 root 11. All right, root 48. If we use the factorization, now I want to point something else to you. How many of you recognize that sometimes when you take out a perfect square, you can take out another perfect square? And sometimes you miss the bigger perfect square because the number's quite big. 48 is a big number. If you use the factorization method, you don't have to worry about thinking like that. By the way, when I factorize 48, I start off with not 2. I know that 6 times 8 is 48. And I know that 6 is 2 times 2. No, it isn't. I know that 6 is 2 times 3. I know that 8 is 2 times 2 times 2. So what I have up here is 2 times 3 times 2 times 2 times 2. And it's a square root that I'm looking at. So that means I'm going to peel out of this radicand anything that is in a pair. So there's a pair here of 2's. In my next step, I'm going to write a 2, a single 2, outside of the radical. There is also, however, a pair of 2's here. So in my next step, I'm going to write a single 2 outside of the radical. Now what do I have left? Well, the 2 blue 2's are gone. The 2 yellow 2's are gone. I'm left with 3. And I can simplify this by taking these 2 2's that are outside of the radical and multiplying them and get 4 root 3. I can tell you right now that if I give this problem to Math 10C students, I say simplify root 48, I get a lot of the time 2 root 12. Because the students look at 48 and they go, oh, wow, 4 goes into 48 12 times, and they're right. And the square root of 4 is 2, so you get 2 root 12. But the problem with that is there's still more work to be done because root 12 can be taken further. And then, bear with me here, you can write this as 2 and root 4 root 3, because 4 times 3 is 12. This becomes 2 times the square root of 4, which is 2, times root 3, which is 4 root 3. And to that student, the amount of work they've done is a lot more work than what I did over here on the left. And I always have the same conversation, and I may have had it with you. It's nice if you can find the biggest perfect square that goes in. Do you agree? But do you also agree sometimes if the number is quite big, finding the biggest perfect square is not an easy job? This is a tool that will always work, what we have on the left here. It's always going to work. Our answer is 4 root 3. Cube root of 400. Now, okay, wait a minute. Stop. Just hang on a second here. If we are going to take the grade 10 approach, which most of you like, I think, then this is what you need to do. You need to break 400 into two factors, one of which is a perfect cube. Well, look, I know from experience that high school math students have enough trouble identifying perfect squares, 4, 9, 16, 25, 36. Do you know your perfect cubes? Probably not. I do. I know what the perfect cube is. But rather than doing it that way, we take 400 and we break it apart. I mean, teachers sometimes do this, or they have different visual ways of doing this. I just start breaking it apart in terms of factors. So I'm not going to do this. I will in a bit. I would probably just go 4 times 100. And I admit that I might take a couple of shortcuts here and go immediately to 2 times 2 times 2 times 5 times 2 times 5. Because I know 4 is 2 times 2, and 100 is 10 times 10. So, again, if you're going to have to rely on your calculator to start figuring out how you can write 10, if you don't know that it's 2 times 5, I don't know how to help you with that. So that is what 400 is equal to, which means the cube root of 400 is equal to the cube root of 2 times 2 times 2 times 5 times 2 times 5. So let's see how this rule works. This is a cube root. According to what I've told you, since it's a cube root, we ought to be able to take a triplet out. And I'll explain to you why this rule is going to work in a second. And I take that triplet outside and I write it as a single. And I write it as a single 2 times the cube root of, what do we have left? 5 times 2 times 5, which is 2 times the cube root of 50. The really nice thing, everybody, about using this method is I can look at 50 and I can go, I know I cannot extract anything else, because if I could, I would have seen 3 more identical things up here. I don't have to go, oh, what divides into 50? I'm done. To explain to you why this rule works, those 3 2's multiplied together give you 8. The 5 times the 2 times the 5 give you 50. The cube root of 8 is 2. Because a cube root is asking you for the number that you cube to get the thing you're taking the cube root of. That's confusing. The cube root of 8 is the number that you would cube to get 8. It's the number that you would multiply by itself 3 times to get 8. Well, that's why we extract a group of 3, but we write it as a single 1. A single 2 is what I mean. Like we write a single item, and that item happens to have a value of 2. Convert all of the following mixed radicals to entire radicals. Now, you were taught different ways to do this, but let's just take what I've taught you already today and put it in reverse. If we have a single number that's outside, if we have a single number that's outside of the radicand, or the radical, then when we put it inside, we're going to have 2 of them. And this is really, there's nothing math 20-ish about this. And then, I don't know why I wrote 15. And then what we have to do is multiply these numbers together. and I get 325, I think. So 5 root 13 is a mixed radical. The entire radical, how can I forget what I just said? 425? 325, thank you. Root 325. 3 root 2. Well, this is really... I want to just write 9. And here's why I wrote 9, and I didn't mean to. I meant to write 3 times 3. I wrote 9 because I know, excuse me, the square root of 9 is 3. So I have a 3 outside. That means I must be taking the square root of 9. But I will follow the rule and write 3 times 3 times 2, and this is root 18. You know, to be honest, very rarely do we want to go in this direction. We almost always want to go in the other direction. And C, 4 cube root 6. So rather than saying, since I have 4 outside of the cube root, what number would I cube root to get 4? The answer is 64, by the way. You simply say, I'm going to pop that 4 that's outside of the cube root inside, but I'm going to put it 3 times. Because the cube root of 4 is equal to, the cube root of 4 times 4 times 4 is equal to just 4. So I end up with this. I want to say 396, but I could be wrong. I'm wrong. Oh, yeah, I'm wrong. 64 times 6 is 360. 384. So we get the cube root of 384. Capiche? All right. So now let's get to some examples. Let's jack it up a notch here to something that's more sophisticated. In other words, something that is at a Math 20-1 level. Express each entire radical as a mixed radical in simplest form, and then here's something new, something different. Identify any restrictions on the variables. Okay. I think I want to leave that just for now and come back to it. Okay. I'm going to introduce the concept of restrictions on variables. I believe I want to do it in B. I do. And if I rewrote this lesson, and I will for next time, I would switch the order of A and B for a reason that's going to get kind of sneaky. So we want to simplify this, and that means what you have to do is write 120 f to the 5 as prime factors. You need to take 120 and strip it down to all of its little primes. 2s and 3s and 5s and 7s. I don't think there'll be 7s. So I'm going to give everybody a minute to do that. We want to write 120 as a series of numbers that are multiplied by each other. And I will give you a hint that I believe there are going to be 5 of them. And if you're like me and you're doing this in your head, just be careful, okay? Because if you always just rely on doing it in your head in one shot, you're liable to make a mistake. So here's my thinking. Those are the numbers, by the way. I'm almost positive of that. And I got that by looking at this number and saying, well, that's 12 times 10. I know 10 is 2 times 5. How many times are we going to do that calculation where we see a 10 and you go, oh, 2 times 5? Are you going to have to, solve that puzzle every time you see 10? Or are you sooner or later going to say it's 2 times 5? The 12 the 12 is 4 times 3. I'm not quite sure why I wrote it as 2 times 3 times 2. But I know 4 is 2 2s and 3 is a 1 3, so this was the process that went on in my head. But you don't need, you know what, you don't even need to write any of that. Even if it were a written response. This would not be a written response, by the way. So what do we have? 2 times 3 times 2 times 2 times 5. How did I do? Is that correct? Bless you. Now what about the f's? Well, if I'm going to factor f to the 5, then I'm going to have to write f times f times f times f times f. And do not snicker to yourself because in your head you know exactly what's going on and you don't need to write that. If you don't need to write that, that's fine. But I guarantee you, other people in the room do need to write it. If you can bypass this and just get right to the answer, I'm fine with that. So what are we going to do with this? F to the 5 means 5 f's multiplied together. We are going to look for triplets. We are going to look for something that occurs as an identical thing 3 times, and we can write that outside the radical. There is something else that occurs 3 times, and I don't care which 3 f's you use. Those 3 f's you look at are going to become 1 f outside, leaving you 2 f's inside. So we have a triplet of 2's, which becomes a single 2 outside. We have a triplet of f's, which becomes a single f outside. And the leftovers are now going to be packed together again in a condensed form. We have a 3 and a 5, which is 15. And then we have f cubed. Nope. We have f squared. We have this left, this left, this left, and this left. And that's the answer. 2f multiplied by the cube root of 15f squared. All right, this one. Well, let's tear this down. I'm just curious, how many of you can see how many f's are going to be outside or how many m's are going to be outside when we're done here? And you know how many m's are going to be left over. That's not everybody. There's only about 5 hands that went up. So what we want to do is rewrite this. Now, I happen to know 32 is 2 times 2 times 2 times 2 times 2. I happen to know that. Because 32 is 2 times 16. 16 is 4 times 4. Each of these 4's is 2 times 2. So we can write 2 times 2 times 2 times 2 times 2. How many of you feel as though you could write 2 to the 5 and finish the problem from here? If you can, then you probably have no need to expand out m to the 7 either, right? But my experience is it's confusing for students. So now I'm going to write out m to the 7. And this gets to be a real pain. m, 2, 3, 4, 5, 6, 7. And it's a 4th root. So what are we looking for? We are looking for a group of 4 and a group of 4. I didn't use different colors here, but it doesn't matter. And all we would have left would be this 2 that I've not highlighted and the 3 m's multiplied together. And there aren't 4 identical things anymore. The 2 is going to become a single 2 outside. The 4 m's, I hate saying 4 m's. The m to the 4 is going to become a single m outside, and we will be left with the 4th root of 2m cubed. By the way, when I write the 4th root, if you look at your handout, that's how it types up on a computer. And that's how it's written in a textbook or an exam. But when I write it, I tend to really I write a big long thing and I put just a little tiny 4 there. You don't want to confuse that 4 with where the 2 or the m is. Now let's talk about restrictions. I'm going to tell you right now, well, 2 things. First, a restriction on a variable is a number that the variable is not allowed to be. Okay? You're not allowed to have certain number operations. For example, you can never divide by 0. So if I had a mathematical expression of 12 over m, I would have to say m is not allowed to be 0. Why not? Because if m is 0, you get slapped on the hand. Well, not by me. I'm not going to slap you on that. But the math gods look at you and they slap you on the hand. They go, you can't do that. You're not allowed to do that. Another thing that we're not allowed to do is we're not allowed to take the square root of a negative number. Not allowed to do that. Now, why is that? Well, you might just remember you can't take the square root of a number, but if I tell you to take the square root of 9, we know that's 3. And the reason we know it's 3 is because 3 squared will give you the 9. So if I said to you, what is the square root of negative 25, I'm asking you for a thing that if you were to square that thing, it would give you negative 25. Just 1 second. I think I know what you're going to ask, but give me a minute. There is no number that you square to get a negative, no real number. So what I'm telling you is this, that in terms of this lesson, the radicand must be greater than or equal to 0. It cannot be negative. I'm going to rewrite what I wrote because you're going to ask me about something here, I think. I wrote root 9 equals 3. Let's see if I got it. What's your question? Oh, you're way ahead of me. We'll get to that. And that's why I want to switch the order of these 2 questions, A and B. Okay? It has to do with whether it's a square root, 4th root, 6th root, 8th root, or cube root, 5th root. There's a difference. Okay. The radicand cannot be negative if this is even. You cannot take the square root of a negative. You cannot take the 4th root of a negative. Because, for example, I totally thought you were going to ask something else. If I said to you, what is the 4th root of 16? The answer is 2. Because 2 is the number multiplied by itself 4 times to give 16. Is there a number that multiplies by itself 4 times to get negative 16? Well, no, because when you're multiplying 4 things together, there is no way this can be negative. Because if this thing is negative, by the way, then when you multiply 4 of them together, you'll get positive. So any time you have an even root of a radicand, this is true. If you have an odd root, who cares? What's the cube root of negative 27? 1 second. What's the cube root of negative 27? Negative 3, because negative 3 times negative 3 times negative 3 gives you negative 27. So, and please don't forget your question, Ariana. For A, there are no restrictions on F. And by the way, you always look at the original question to get your restrictions. There are no restrictions on F because it's a cube root. It's got nothing to do with how many F's are in there. However, for B, we have to say that M must be greater than or equal to 0. Because you're not allowed to take a 4th root of a negative number. There are twists and turns here. Go ahead.
What if they're all negative, but then they multiply again? Like, what if the square root of...
You may encounter that, but even if I had, let's say I had the square root of negative 2 times negative m. Is that what you're saying?
Like the square root of 9 is negative 3.
Okay, it gets certainly more complicated. If we had this, then what we would do, and you're getting beyond where we want to be for sure right now. If you had this, then we would say negative 2m must be greater than or equal to 0. Because this thing cannot be negative. The whole thing can't be negative. But if you divide both sides by negative 2, and switch the sign, I hate inequalities, and switch the sign because when you divide by a negative you switch it, you discover that the restriction here would be m could be 0 or negative. If we had, and we're getting into 2 or 3 lessons down the road, okay? If we had this, then you would say 2 minus x must be greater than or equal to 0, and you would solve this for x. The only reason, well, I'm going to back up. The only reason why I'm saying the variable has to be positive is because there's multiplication occurring everywhere here. Okay. If I had something like this, 2 minus x, it's more complicated. And that's why I've told you that the safest bet is just say the radicand must be positive. I hope that answers your question. Okay. The restriction thing is very complicated. It really is very complicated. Let's simplify this first, and then we'll talk about the restrictions here. You have the square root of 63. I believe 63 is 3 times 3 times 7, because 63 is 9 times 7. And then we have 7 n's. Feel free, if you do not want to write these, but you know what's going to happen, to not write them. 1, 2, 3, 4, I need 2 more. And then 4 p's. I hope you see that if you can come up with a shortcut, man, that's a lot better than having to write this each time. And I'm going to show you the shortcut now. We have 3 times 3 times 7. And I have n to the 7. So I have n squared, n squared, n squared, n to the 1. Why did I break them up that way? Because I'm taking the square root, so I want to look at pairs of n's. And n squared is going to become 1n outside. The p's, well, I hope you guys see there will be no p's left under the radical. Right? Okay. So we can take a 3 out. We can take an n, an n, an n out. You know, to be honest, I don't like this. I don't like this second line I've written. It's confusing to me. I would rather look here and say 2 n's become 1. 2 n's become 1. 2 n's become 1. 1, 1, 1. And then we bring out a p and a p for each of those, and we're left with the square root of 7n. Okay with that? Okay, now the restrictions. N must be greater than or equal to 0, and I'm looking up here. I'm not looking at the bottom. If you look at the bottom, you will get the right answer in this question, but I don't want you to look at the bottom, because you won't always get the right answer by looking there. I do not have to put a restriction on P. But the reason I don't have to put a restriction on P is not because there's no P's left over. That's not it. Because sometimes you will have P's left over in these questions, but you still don't put a restriction on P. Look at the top line. Why don't I have to say what P is? This is really tricky. Isaac? Right, because p is raised to an even exponent. And this is a different thing than we were discussing before. I'm not talking about this number here. Isaac and I were talking about this number 4. P to the 4 means it doesn't matter what p is. When you raise it to the 4, it's going to become positive, and you can take any root of any positive number. And again, it has nothing to do with the fact that you have nothing left here. Sometimes you might have some things left here even though p was an even number or raised to an even number. So that's it. N is greater than or equal to 0. Convert each mixed radical to an entire radical. Well, the 4x is outside of a square root, so we're going to put it inside of the square root twice, where it will join forces with the 3x that was already there, and then we can pack that thing together and write, I believe, 48x cubed. Good. The square root of 48x cubed. X is not allowed to be negative, so x has to be greater than or equal to 0. J to the 4 cube root j. I don't know. I'm just curious. How many of you feel as though it should be j to the 13 underneath? This is a cube root. So anything that is, there's my j that was originally there. Anything that was outside gets put inside 4 times. So I have j to the 4 times j to the 4 times j to the 4 under the radical sign, joining forces with the j to the 1 that was already there. When you multiply exponential expressions or terms that have the same base, the base remains the same, and you add the exponents. 4 plus 4 plus 4 plus 1 is 13. Do I put, I want to check something here. We're okay. Do I have to state a restriction for j? So the first thing you look at is the exponent on j. If it's even, then you don't need to. Well, it's odd, so maybe I should. But then we look at the exponent, not the exponent, were some of you kind of balking at my earlier question because I forgot to put a 3 here? Is that what the problem was? I should have put a 3 here. Since it's a cube root, I don't have to worry about restrictions. I can take cube roots of anything. (2k squared, 4th root 4k). So we have the 4th root, and we have a 4k. We have a 2k squared outside, so we're going to put it in 4 times. Because it's a 4th root. And then we also have the 4k underneath here. What do we get? 2 times 2 times 2 times 2 times 4, 64, I believe. K to the 9. Any questions with that set of problems? Right? Simplify if possible. What on earth does this mean? I mean, it's just numbers and roots, but if I had 7 puppies and I added 3 puppies, I'd have 10 puppies. I'm not trying to talk down to you. I'm not trying to be sarcastic. I'm being sincere. If I had 7 puppies and I added 3 puppies, as well as an enormous amount of happiness in my life, I would have 10 puppies. When we see 7 times root 5 plus 3 times root 5, that means 7 root 5s plus 3 root 5s. You know, not nearly as entertaining or life-fulfilling as puppies, but you have this. have 2, 3, 4, 5, 6. We've got 7 of those, and we're going to add 1, 2, 3. That's what 7 times root 5 means. Did I get it right? Yeah. That's what 7 times root 5 means. It means 7 of those things. So because these two pieces are the same thing, these two terms are what we call like or similar terms. And I get 10 root 5. This is no different than saying 7x plus 3x is 10x. It's no different than saying 7 pi plus 3 pi is 10 pi. So the answer is 10 root 5. (18 root 14 minus 17 root 14). Well, if I had 18 donuts and I subtracted 17 donuts, other than a whole bunch of shame and eating 17 donuts all by myself, I would be looking at one donut left, right? So it's the same idea. I'm not going to draw 18 root 14s and subtract 17 of them. You get 1 root 14. Does that make sense so far? Okay. 4 root 7 plus 5 root 10. Go ahead, Kendra. No. In case you didn't hear Kendra's question, do you have to write the 1, is what she asked. And I'm saying no. I just put it there because some people would go, well, why is it root 14? I wanted to highlight that it's 1 root 14. Yeah. 4 root 7 plus 5 root 10 is like me saying add 4 donuts and 5 puppies. What do you have? You have 4 donuts and 5 puppies. You can't puppies. You can't combine them somehow into some new unique thing. So this is done. You cannot do anything with this. They're not like terms. Well, what about this? Can we subtract these? Well, no, because they're not like terms. But can we simplify root 18? Can we break root 18 down? And since it's a square root, I'm just going to go with 2 numbers. Can you find 2 numbers that multiply to give 18 where one is a perfect square? It's 9, right? So I would write root 18, I'm going to write it this way, as root 9 root 2. Can I do the same kind of thing with root 8? Yep, I can break it into root 4 root 2. You know the thing where I write, 2 times 2 times 2 times 3 times all that stuff? I'm not going to do that with small numbers if it's a square root. This becomes 4. The square root of 9 is 3 root 2 minus 2 root 2. This 4 and this 3 are both coefficients. They're not radicals. And I can multiply those two together to get 12 root 2 minus 2 root 2. And now they're similar things. I'm subtracting root 2's to get 10 root 2. Questions with D? Right? Root 18 plus root 32. So I would like everybody to simplify root 18 and root 32 first. And I'm sorry, keep going. So for those of you that basically look at root 18 and say it's 3 root 2, I would just caution you to be careful not to make a mistake, not to go too fast. What's happening here is you're breaking 18 into 9 and 2, and the root 9 becomes 3. You're breaking root 32. I hope you can break it into root 16, root 2. If that's troublesome for you, then you're going to have to write 32 as 2 times 2 times 2. You're going to have to break it down that way and extract pairs of numbers. So root 18 is 3 root 2. Root 32 is 4 root 2 because the square root of 16 is 4. So we get 7 root 2. Are these like terms? No. I don't know quite how to say this. We have 1. You don't need to write this. You have 1 square root 4c cubed. And you're subtracting 5 square root 9c cubed. Square root 4c cubed is a different thing than square root 9c cubed. They're not identical things. But can we simplify these? Well, yes, because the square root of 4 is 2, so I can put that 2 outside and have 2 square root c cubed minus, this is one area where you can make a mistake by skipping steps. How many of you would just write minus 15 square root c cubed? Be careful, because very often I see 45 here. People will put 45. Good students will put 45 because they're skipping a step and they're missing something. Some little link to the problem has gone in their head. This is 5, and then the square root of 9 is a 3 without the square root, and then square root c cubed. The 5 times the 3 gives 15. So we get this. And are these things like terms? Yes, they are square root c cubed. That's what we're doing. We've got 2 of them, and we're subtracting 15 of them, which gives me negative 13 of those things, which are square root c cubed. By the way, c must be greater than or equal to 0 because you're taking a square root. Yep.
Can you not simplify the c cubed into a c squared and a c?
Definitely. That's something I should have looked at. Because c cubed has 3 c's multiplied together, we can pull out 2 of them. And I guess I could have done that up here. I'm kind of glad I didn't because it might be easier to see when there's just 1. So this is negative 13. You know, feel free to write c, 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 and then take out a pair of c's. Or you can write c squared times c, and the square root of c squared is c. This gets harder to explain what we have. I would say that we have negative 13 of these. We have negative 13 c root c's. I don't think you want to say we have negative 13 c root c's, although it's not wrong, it's just a little more weird. Oh, smokes. Well, all that simplifying radicals, that's what you need to do to these 4 pieces to find out which ones are similar to which ones. So I'm going to give you a minute here. You want to break this down and see if you can find out what root 98 can be written as. Root 10, there's nothing to do there. The minus 5 root 8 can be broken down. Minus 3 root 40 can be broken down. And remember, you're looking for 2 numbers, one of which is a perfect square. And by the way, example 4, I meant to remove it from this lesson. So there's some other wild looking ones. Don't have to worry about that. We're just going to do this one and then one more. And the core material here is not difficult. There's just a lot of numbers, right? It's so easy to just mess up one number. 98 is divisible by 49. Again, if you don't see or you don't know that 98 is divisible by 49, which is 7 squared, then you might have to break 98 down into like 2 times 7 times 7 to see that. The 8 can be broken into a 4 and a 2. 4 is a perfect square. The 40 can also be broken into a 4 and a 2. This is 2 times 7 root 2. And I want to go super slow here. The 2 and the 7 are both not radicals, so I can multiply them. And I would really caution you. I know that some of you can go from here directly to here. I know that. I can do it. And some of you are just as good at numbers as I am, maybe even better. But I caution you not to do that unless you're sure. It's so easy to make a mistake. And I don't know, I'll just throw this out here. How many of you look at this and say, well, I'm going to move a 7 outside. 7 times 2 is 14, and I'm left with 2. If you see that, that's great. But be careful. Then we have plus root 10. I'm going to write 1 root 10, although we certainly don't need to put that 1. This is minus 5 times 2 root 2, so it's minus 10 root 2. Starting to see some pattern here that we have root 2's we can work with. And then over here, this is minus 3 times 2, 10. 3 times 2 is 6. More stuff we can combine. So we end up with root 10's and root 2's. Let's see. 14 root 2 minus 10 root 2 is 4 root 2. 1 root 10 minus 6 root 10 is negative 5 root 10. And that's the answer. So the last one, again here with square roots, I think going directly to something like this is the way to go, rather than writing 40 is 2 times 2 times 2 times 5. But cube roots, I wouldn't do that. We need to take 16 as a cube root radicand and simplify it. And your first step is to figure out what 16 is. Well, 16 is 2 times 2 times 2 times 2 because 2 times 2 is 4. 2 times 2 is 4. 4 times 4 is 16. 54 might require a little more work. We've got a 5 here, cube root. Let's see, 54 is 9 times 6. That one always gave me trouble in school. 9 times 6 is 54. So 9 is 3 times 3. 6 is 3 times 2. These are cube roots, so I'm looking to extract a triple. And if your 3 3's were not written beside each other, then it doesn't matter. You could have them separated by numbers. This becomes 2 cube root 2 plus 5 times 3 cube root 2. I don't think there's anything wrong with just writing 17 cube root 2. Although I know there would be some people in the class that would be going, well, where did he get that from? Because 5 times 3 is 15. So we get 2 cube root 2 plus 15 cube root 2. $2 plus $15 is $17. So it's 17 cube root 2. And that's it. Again, I don't want this one in here. For practice, there's a section on page 278, which kind of covers the basics. Well, it's all basic stuff. On page 304, I've got 1 to 5, but you can make a note that that's just extra. If you need extra practice, that's what you can look at doing.